So for phi 2, the difference, as I said, was you now have an equal sign. And we're not solving for anything yet. We will get to solving after the winter break. Right now, you're just verifying or proving that the left side equals the right side. And I will tell you that in Math Excel, depending upon how they ask the question, if they say prove the identity, they're going to require you to put in reasons, like in a geometric proof, reasons as to why you just did something. So if I substitute in something, as we did in 5-1, I substitute 1 minus cosine squared in for sine squared. That's using a Pythagorean identity. So that would be an answer choice that you can select from. I think when you go through Math Excel, it won't be an issue for you to figure out what the reason is for each of these steps. I am not going to require that on my test this week, but I don't have any issues with making you do it for homework because it's good practice. You think about where did they come up with that? How do they do that? Did they use a reciprocal identity, diagonal identity? Did they use discipline substitution? Did they find the least common denominator of a fraction? What did they do from start to step? Kind of makes you think about it. And the nice thing about doing this homework in Math Excel versus on your own is at least you have some idea of where to go. You might have a multiple choice option of 4 different choices, and you have to go through each of the 4 answer choices and look to see, did they make legal substitutions? Are they verifying it correctly? And it shows you, or at least will make you think of different strategies and see ways that somebody else has solved it. There are open response ways afterwards in there as well. But the nice thing about Math Excel is it gives you an idea of where to start. Whereas if you'll see on here, when you do them all by yourself, it's kind of a shot in the dark. So here are some guidelines for verifying. And we've talked about some of these guidelines before. The first guideline, work with one side and one side only. Well, which side do you work with? My suggestion is it's better to work with a more complicated side. It's easier to make complicated things into a simpler item rather than take a simple item and make it more complicated. It's much easier to go from complicated to simple. And so the question arose in a previous period, well, what if I choose the wrong side? That won't matter. You can verify these identities by using either side. It's just easier if you choose the more complicated side. Step 2 says look for opportunities to factor an expression. So we've talked about that before. If you can factor something, factor it. If it's already factored, multiply it. We also talked about changing everything to sines and cosines. If you have 2 different fractions, add them together, find the LCD. If you have a binomial, we'll do this today, square it out properly. A binomial a plus b quantity squared is not a squared plus b squared. It has a middle term. Or create a monomial denominator. We'll do that today as well. So you have a binomial denominator. We're going to create that and convert it to one monomial. There's a reason for that. Step 3, look for opportunities to use the fundamental identities. Those are the identities from 5-1 that you're getting tested every time. We're looking for places that we can always do equal substitutions for those. Note which functions are in the final expression you want. So if I'm working the left side of the equation, I'm always looking at the right side to see where do I have to go. Here's what I've got. The right side is telling me where to go, or vice versa. If I'm working the right side, look to the left side. It's telling you where you need to go. It's helping you with your map and your route that you're taking to get there. Sines and cosines pair up well, and we can see this in the Pythagorean identity. Sines and cosines are not Pythagorean identity. There's another Pythagorean identity that has secants and tangents. And then the final one has cosecants and cotangents. So they always pair up well, because if I can convert them into something that looks like a Pythagorean identity, I can swap them out. Number 4, if the preceding guidelines do not help, try converting all terms to sines and cosines. That's something that you learned in 5-1. Doing something is better than doing nothing. Try something. At least it tells you what didn't work. And then you're left with, have this out with you when you're doing your homework, and when you get stuck and frustrated, go through these and look to see, can I do any of these items to help get me unstuck? And if you try to come up with a dead end, just cross it out and start all over again. And that's where the frustration comes from. Well, I tried one thing, it didn't work, so I'm done. No, try again. So, practice makes perfect. And in fact, when you're doing your Math Excel, and to get ready for your test, you can always click on similar example. So depending upon who you are, if you're not comfortable with the work, click on similar example. You can do it up to 5 times until you feel more comfortable with it. You can also go to study guide and take the quiz me's. Those are 5-question quizzes, and you can keep reloading those quiz me's until you feel comfortable with those questions and how they work. And for every one of you, it's different how much practice that you need. But it's all available there for you. So let's start with example 1. And verifying an identity just means that we're trying to make the left side look exactly like the right side. Which is the more complicated side, the left or the right? The left. So that's the side we're going to start with. We're not touching the right side, but it is going to constantly be brought down. You cannot ignore it completely. You have to always bring it down. Every time you do a step, rewrite both sides. So in here, I've got a couple of options. I see secant squared. I love things that are squared. Why? You can factor them out, possibly, or what else? Pythagorean identities, you can replace them. I could replace just secant squared with what? Look at your Pythagorean identities. Yep. Just secant squared can be replaced with that 1 plus tangent squared, right? So I could replace both of those secant squareds with a 1 plus tangent squared. 1 plus tangent squared here, minus 1 plus 1 and minus 1 cancel, and be left with a tangent squared. Oftentimes I don't necessarily want to substitute both of them out, because then I might end up with something more complicated. I'm trying to go for simple. Or I could substitute this entire numerator with what? It's your identities. Could I get one side to be secant squared minus 1? Here's my secant squared. How do I get secant squared minus 1? Subtract the 1. Wouldn't I be left with tan squared on the other side? So that means I could completely substitute this out for just tan squared. I like that because it's simple. So let's try that. So we're going to take all of that and we're going to replace it with just tan squared of theta. And I'm going to leave the denominator alone. Mostly because I know I'm trying to get to sine. And so I want to make it as if I can even talk, as least complicated as possible. So from here, what could I do? I don't want to go back and use my Pythagorean identities at this point, because it's going to give me something with a plus or minus 1. And that makes it more complicated. Because right now I have like one fraction. And it looks kind of simple at this point, except it's in tangents and secants. I want sine. What do I do? Very good. I can convert to sines and cosines, right? That's one of our popular strategies employed. So for your note purposes, I want you to write this out because you're going to forget when you go home how we got this. Tangent squared becomes sine squared theta over cosine squared theta. And then times, and for our note purposes, we're going to write this out as 1 over secant squared. We could have skipped this step, this interim step right here. But I want you to understand note-wise where you're coming from. And as Sam said, 1 over secant squared can be converted to what? And so this gets converted to cosine squared over 1. Because remember, this is the reciprocal identity. We're going from 1 over secant squared to cosine squared. And you can kind of help yourself remember that because you know you got to get to sine squared and you know they kind of have to cancel out. So it kind of help you remember that. Equals, don't drop off, but don't ignore the other side of your equal sign, sine squared. Now why did I go through all that? So I can do what? I can cross out both of those cosine squares. And I'm left with sine squared theta equals sine squared theta. I only work one side and the left side is exactly equal to the right side. That's my goal. That's not to say that this is the only answer. You could have chosen to work the right side to come up with the left side equaling secant squared theta minus 1 over secant squared theta. I would prefer not to do that. It's a lot more complicated. What I don't want to see is you starting on the left and then moving over to the right and working both sides at the same time. You choose one side, the left side or the right side, and only work one side. Do not work both sides. There is a situation where I'll allow you to work both sides, but typically I don't want you to do it. Okay? Questions on that one, why we did anything, how we got something, really good? All right, let's look at 2. One of our strategies is if we have fractions, and we have multiple fractions here, is to combine them into one fraction. And wouldn't you agree that the left side is definitely more complicated than the right? So that's the side we're going to work with. If I am to get these into one fraction, what do I have to do first? I have to find my LCD. And haven't we done this particular LCD twice already? I've got 1 minus sine theta, 1 plus sine theta. Isn't that the difference of 2 squares factor pattern? Isn't my LCD 1 minus sine theta times 1 plus sine theta? And then I want to multiply top and bottom of each of these by what they're missing. So this denominator is missing 1 plus sine of theta. So I want to multiply numerator and denominator by that. The second fraction is missing 1 minus sine of theta. So top and bottom get multiplied by that. If in doubt, write it out. Show all work. So we're going to multiply the top together. So these two get multiplied. You're just left with 1 plus sine of theta over that LCD. Don't multiply the LCD out yet. I wait to multiply things to see if it's going to do me any good, because otherwise I just end up doing more work. And so I've got 1 plus sine of theta, 1 minus sine of theta. Then plus, multiplying that out, I get 1 minus sine of theta. Over the LCD, 1 plus sine theta, 1 minus sine theta. And don't forget about the right side. So the right side is 2 secant squared theta. Now that I have the same denominator, can't I combine like terms? These are like terms, 1 plus 1. There's my 2 I'm looking for. And then what's going to happen with a positive sign and a negative sign? They cancel each other out. A positive and negative cancel each other out. It's not like reducing a fraction canceling out, it's just it's an opposite. So it's over the same denominator, 1 plus sine of theta, 1 minus sine of theta, equals 2 secant squared of theta. Now I have to look at my left side again and decide, do I want to multiply out that denominator? Because I'm trying to get to a secant squared. I got the 2, but somehow this down here, all of that has to become a secant squared. Secant squared screams what? Pythagorean identity, right? We should know by now that when we multiply the difference of 2 squares factor pattern, we might get a Pythagorean identity that we can use. And let's see what happens here. So I'm going to multiply that out. This is a plus b, a minus b. It multiplies out as a squared minus b squared. So the first term squared is 1 minus the second term squared would be sine squared theta. If not, FOIL it out. You get the same thing. Your inner and outer terms are going to cancel out. You're left with just your first term squared and your last term squared minus. Equals 2 secant squared theta. This should be screaming, look at me, look at me, look at me. Why? That equals cosine squared, doesn't it? If I take my sine squared plus cosine squared equals 1, I can make it into this by subtracting sine squared from both sides. So I can replace that with 2 over cosine squared theta equals 2 secant squared theta. Then just for note purposes, again, this is a step you could have skipped that we're going to do for this next step. But I want you to understand that this 2 is really 2 times, this is 1 over cosine squared theta equals 2 secant squared theta. What's 1 over the cosine really equal? 1 over cosine squared. Secant squared. That's a reciprocal identity. So we've got 2 secant squared theta equals 2 secant squared theta. I have the left side equaling the right side. Notice I never touch the right side, I only work the left. Do not jump over and work left and right at the same time. Again, that's not the only way that I could have done this. There are definitely some different avenues along the way that we could have chosen to do something different. If something doesn't work for you the first time, backtrack and go back and do something else. Issues, problems, concerns with that. You don't understand how we got something. Okay, so flip it. Let's look at example 3. What side's definitely the complicated side, left or right? The left side. Now, we have as one of our strategies said that if something's not multiplied, this is factored, right? The left side's factored, that perhaps the strategy would be to multiply it out. My issue with that is, do tangents and cosines go together? No. That's probably why I'm not going to. And furthermore, I have a tan squared with a 1 and a cosine squared with a 1. What does that scream at you? But they're my identities. So let's see what those would give me. So you have to be careful with these. So I'm going to zoom out a little bit. Tan squared plus 1. That's an exact substitution. I could substitute this entire thing with secant squared with no manipulation, right? This, however, does not substitute out as sine squared. You have to be careful. How can I make this into cosine squared minus 1? I have to subtract the 1 and then move the cosine. So we're going to do that one by hand because that's 2 steps in our head. We're going to take this and we are going to manipulate it up here. So everybody can see where we're coming from. So if I want to get cosine squared minus 1, I want this minus 1 here, or this 1 here, to get over to the other side of the cosine. And I can do that by subtracting 1. This right here gives me that cosine squared minus 1, but I have that pesky sine squared over there. So I want to subtract the sine squared in order to move it. And so that's why we end up with that cosine squared minus 1 equaling a negative, and here's the key. Sometimes we end up with a negative sine squared. And if you look, we're always supposed to be looking at the other side that we're not touching, this has a negative in front of the tan squared. The only way to get that negative is because of this right here. So we're going to replace tan squared plus 1 with secant squared of x. So that one was a straight substitution. But the cosine squared x minus 1 gets replaced with a negative sine squared of x equals, don't forget the right side. Again, I don't want to resubstitute this or this. I want to think about converting everything to sines and cosines because I'm trying to get tangent. I don't want to go over to the right side and convert tangent squared to sine squared over cosine squared. And then work this. I don't want to be working 2 sides, work 1. I can change secant squared into what? 1 over cosine squared of x times, and again, this is a step that we're putting in purely for your notes. You could have skipped this specific step here and gone directly to the next step. Well, you can either have this step or the next step. You have to have one of the 2 next steps. And so what this gives me is negative sine squared x divided by cosine squared x is equal to negative tan squared x. So I have to see one of these two steps, but I don't have to have both of them. You can't go from here to the answer. Let's just put it that way. You can go from here to here, or from here to here. And then from here, what is sine over cosine? Tangent. So now we have a negative tan squared x equals a negative tan squared x. And again, if you're not sure if I should show the step, well then show the step. All of these are employing different strategies or strategies in different orders. You can't get good at them unless you start practicing and using them and learning from them. Learning what to do, what not to do. Number 4. What side do you think is the more complicated side? The right side actually is, because it's got a fraction. That tends to make it harder. So here's a new strategy for you. I have a fraction that I want to break into two different terms that are not fractions. In order to do that, I cannot take and put cosine over 1 minus cosine over sine. You cannot break up the denominator of a fraction into two different pieces. If this were flipped, I could do that. But you can't break up a fraction except by taking pieces of the numerator and putting them over the entire denominator. So I want that denominator to be a monomial. So in order to do that, I want to switch this, or I want to multiply this by its conjugate. Usually if I multiply a binomial by its conjugate, I'm going to get something that is squared, and you notice there's a 1 there, which means I can then use a Pythagorean identity. So I'm going to multiply top and bottom by 1 plus the sine of x. You might want to write yourself a note to obtain a monomial denominator. Multiply by the conjugate, and then use a Pythag ident. So use a Pythagorean identity. A conjugate just changes the middle sign. Only the middle sign, not all signs. So don't change the 1 to a negative. Alright, so again, I'm going to ignore the left, although I'm going to keep bringing it down, knowing that I want to get to secant and tangent eventually. So the left is secant of x plus tan of x equals, I'm going to hold off on multiplying until I see if it's to my advantage. So I'm going to wait. So I've got cosine of x times 1 plus sine of x. The reason why I did this was to multiply the bottom. I specifically did that to multiply that together. So that's your difference of two squares factor pattern. A squared is 1 minus b squared is sine squared x. This should be screaming Pythagorean identity to you, right? How can we get this to become 1 minus sine squared? Subtract that sine squared and you get just cosine squared. So that's what we're going to replace it with. So the left side doesn't change. You don't want to touch it. And then I've got cosine of x times 1 plus sine of x, all divided by, and this whole thing gets replaced with cosine of x. You see why I might not have multiplied that top, the numerator? Because I can do what with it? I can cancel anything that's being multiplied with something else, one with the numerator, one with the denominator. This is a cosine of x, this is a cosine squared of x. It's no different than having a y and a y squared. I can just use exponent rules. So I can cancel one of these with one of those. So I'm left with secant of x plus tan of x equals that whole numerator, 1 plus sine of x, over just 1 cosine of x. You're thinking, well, how does that help me? Well, I now have a denominator that is a monomial. That I can split up into 2 different fractions because I've got 2 different terms there. All along I've had 1 fraction that I have to split up into 2. I cannot split this into 2 terms because it's 1 term, cosine over that. That's the only thing you can do. But this, I can split into 2 terms. So let's split it. I've got the left secant of x plus tan of x equals, each term in the numerator goes over the entire denominator. So 1 over the whole denominator plus sine over the whole denominator. So that's that fraction. Once I get that monomial denominator, you can split it into multiple fractions. What is 1 over the cosine of x equal to? Secant of x. Isn't that what I want? And what's sine over cosine? Tan of x. So I now have the left side equaling the right side. I have verified that identity. Again, not the only way that we could have gone about this. Questions, issues, concerns with that? Are we good? All right, so let's look at 5. Here's an example where you can work both sides separately, and you kind of start and stop and start and stop. What kind of problem is this versus the other ones that we've done? So fraction equaling a fraction, which makes it a proportion. This is a proportion. A proportion are types of problems you might work both sides. This is not to say that you have to, but you might. Sometimes you're going to want to cross multiply to break apart the fraction. And in this case, it might seem like a good idea until you look at full cross products. Here, I can multiply these two, thinking to myself, cotangent is cosine squared over sine squared times the sine squared. That's viable because I could cancel a sine squared with that. I could end up with something that might be usable. I don't know. Here, it almost looks like the difference of 2 squares factor pattern because it's got a plus minus, but do cosecants and sines typically go together? No, definitely not with a Pythagorean identity. I know that sine and 1 over cosecant are reciprocals of each other, but it's not going to do us a lot of good here to multiply that out. So I'm probably not going to cross multiply, but that is a possibility with a Pythagorean or with a proportion. So instead, I might look at each side differently. Notice here how I have a monomial in the denominator. Couldn't I break apart this fraction like we did in example 4, halfway down, break apart this into 2 different fractions? It's a possibility, it's a thought. That means I'd have to break this into 2 different fractions, but I can't yet. But could I make this into a monomial denominator? Where I could do that? Yes, I could. What do I do? Well, multiply by the conjugate. So the conjugate to this is 1 minus cosecant of theta. And I want to do that to top and bottom. This is only one strategy. It's not the only way. Now, as we learned before, I may not want to actually multiply that out that top. So I'm going to hold off, and we're going to leave it as 1 minus cosecant of theta times cotangent squared of theta over, I definitely want to multiply out the denominator. That's the difference of 2 squares pattern. It multiplies out as a squared minus b squared. So 1 squared is 1 minus this squared is cosecant squared of theta equals 1 minus sine of theta over sine of theta. I'm waiting to get a monomial denominator here because I want to compare the two. Because this could be a dead end. We might have to restart over. But this should be screaming out at you. Scream, 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 scream. But be careful. Let's go out a little bit here. Can I make one side of this Pythagorean identity into 1 minus cosecant? I can, but it's kind of like example, what was that one? 3, right? So if I want to do 1 minus cosecant, I've got to move the cosecant. So move the cosecant squared. So that gives me 1 minus cosecant squared plus cotangent squared equals 0. How do I get this by itself? Subtract that cotangent squared, and then I end up with 1 minus cosecant squared theta equals a negative cotangent squared u. So that right there gets replaced with a negative cotangent squared. So you have to be careful when you manipulate those identities that you're doing them correctly. So that's what I'm going to use. And let's just see if it does us any good. So that gets all replaced. Again, I'm not going to multiply this out. 1 minus cosecant of theta times cotangent. Oh, I have a cotangent up there, right? And I'm replacing this with negative cotangent squared theta equals 1 minus sine of theta over sine of theta. Now I have two denominators that are monomials. But in addition to that, what do you notice about that? They can cancel out completely, can't they? This is being multiplied to something, so I can cancel out the cotangent squared, and this is part of the denominator. But be careful when you cancel it out, and this is for our note purposes. You could flip this stuff. I've got 1 minus cosecant of theta over a negative 1. That negative 1 does not cancel out. Equals, at this point I might want to start working the right side. Can't I split this into two different fractions that has a monomial denominator, which means I can do that? And this becomes 1 over the sine of theta minus sine of theta over sine of theta. Then I'm going to take this negative 1 here, and I'm either going to divide it or multiply it to everything. Dividing or multiplying by that negative, it doesn't matter which, you have to choose. They both give you the same thing. If I divide this or multiply by negative 1, it becomes negative 1, and this becomes positive cosecant. So I get negative 1 plus cosecant of theta equals, 1 over sine, cosecant of theta minus 1. Do these look identical? Not yet. You do have to have them looking visually identical, but I can use the commutative property and switch those around. And so I can write cosecant of theta minus 1 equals cosecant of theta minus 1. The only time I really want to see working both sides of an equation is if you have a proportion. Really the only time I want to see it. And on this particular problem, again, that's not the only path that we could have taken. So take a deep breath in through your nose. Out through your mouth. Don't you feel relaxed now? Last example is a little bit hairy. And the last example, we use a lot in calculus, and it looks fairly complicated. And in fact, you might think at first glance, based upon everything that I told you, that we should work the right side first. No. Look at what you have. You have a bunch of sines and cosines, and look at what's inside the parentheses here. You've got sine squared, sine to the 4th, sine to the 6th. Isn't that in ascending order, smallest to largest? And you have this little lowly cosine out here. This is an unusual situation where I'm going to work the simpler side first. And here's why. I have a sine squared, and I have this cosine to the 5th. If I can convert everything into squares, I might be able to use some Pythagorean identities to get the majority of sines. So I'm going to take this, and I'm going to think of it in terms of not cosine to the 5th, but I want this lowly cosine out here. I want to pull out a cosine. So I'm going to think of it as cosine to the fourth x times cosine of x, because I want that lower cosine, trying to make the left and the right side look alike. And that way I can pull the cosine out and just leave it out and deal with sine squared and cosine to the fourth. So if I do that, I'm going to leave sine squared as it is. So here's my sine squared of x. But I want to write the cosine to the fourth as cosine squared x of something raised to an exponent. And why would I want to cosine squared in here? Notice I want all sines in here. I got cosine squared in here. Can I convert that to something? What? 1 minus sine squared. And that'll give me all sines and one little lowly cosine, which is what I'm striving for. But I have cosine to the fourth. So if I want cosine squared in here, what's the same as cosine squared to what power is cosine to the fourth? That would be squared, wouldn't it? And don't forget your cosine of x equals. So we took the cosine to the fourth, converted it to cosine squared squared, that's cosine to the fourth, times that cosine. We're not touching the right side, so just rewrite it. Pretend like it's not ugly. Don't even think about it. Then I want to do a direct substitution here using my Pythagorean identities. So I've got my sine squared of x, but this gets replaced with that 1 minus sine squared of x, and don't forget it's still squared, times cosine of x equals. Write out the whole right side. This is where the sign begins. Really? Do I have to? Yes. And here's where the hard part comes into play, really. This is the only hard part. Once you get used to this process, because you've got about 3 problems in Math Excel that look like this, and they're kind of towards the end. And you'll recognize them because they're going to look like this original problem. They all kind of look the same. Remember when I square this, because nothing here is squared, I need to multiply all of this out so it looks like this. But when I have to square this first before I can multiply it by this. This is not, when I square this, it is not 1 squared minus sine squared squared. It is 1 minus the sine squared of x times 1 minus the sine squared of x. That's what this is. And we're going to do that out by hand, slowly. But we're not forgetting about the sine squared and the cosine. So start with your sine squared. Write that in there and forget about it. Then we're going to multiply out this binomial, FOIL it. 1 times 1 is 1. 1 times negative sine squared, negative sine squared of x. Negative sine squared times 1, negative sine squared of x. And then negative times a negative is a positive. What's sine squared times sine squared? Sine to the fourth. Squared times squared, add the exponents, you get to the fourth. And then in brackets, cosine of x equals. Okay, I've officially run out of room, so I'm going to put my other equal sign down here. Sine squared of x minus 2 sine the fourth x plus sine 6 times cosine of x. Then we're going to collect like terms with this in here. And I'm going to write it in ascending order because this is in ascending order here on the right side, and I know that that's the order I want to get it in. So when I collect like terms, I want it in smallest to largest. Well, a constant is your smallest. So So there's your 1. Don't these two add together? They're like terms. They're both of the sine squared. If I have a -1 and another -1, how many do I have altogether? Sarah, how can you even see what I'm doing with the first second? I never write that way. It'd be more quick in my mind. So how many do I have? -2. Sine squared x's. -2 of them. The variable doesn't change, only the coefficients in front. And then plus sine to the 4th of x, cosine of x equals. And then we have the whole right side. So again, I'm going to run out of room. I'm going to drop it down a little bit. Look closer though. Now what do you think is left? I have my cosine. Those are the same. But these are not. Yet. What's left? Distribute. All you do is distribute. You're going to multiply this into all 3 of these terms. And look at what we get. Sine squared times 1 is sine squared of x. A positive 1 times a -2 as your coefficients gives you a -2. And then sine squared times sine squared gives you what? Sine squared times sine squared. Sine to the 4th x. And then what is sine squared times sine to the 4th? Sine to the 6th x times cosine of x equals sine squared x minus 2 sine 4x plus sine 6x times cosine of x. Doesn't the left side, as ugly as that is, equal the right side? That's a C for cosine. So there's like 3 of those. I'm sure you're going to ask me about one of them tomorrow or the next day. And we'll go through them again and again and again until you get used to it. It's the same process. They don't change. You take whatever this one is over here and convert it so that it could be sine or cosine, tangents, cotangents, secants, cosecants, could be any of those. And convert it so that you have that item squared to that power with one of them pulled out if needed. So make sure you have your notes handy when you're working on problems. You'll identify one as being similar and you can use a similar strategy.